All right, so we're studying electricity. These concepts are going to be a review of grade 9, but grade 9 was 3 years ago. So let's go over it nice and slow. Okay, so in this diagram, it shows a simple electric circuit. Okay, the four main parts: we need an energy source. We need some sort of load, which will convert electrical energy into some other form of energy. We have a switch to control the circuit. And of course, we have conducting wires. Okay. So here I have some diagrams. And there are two different types. Now, we talked about two different types in grade 9s, but just as a reminder, one is a series circuit and one is a parallel circuit. Okay, you can think of parallel like when we draw it like this, you can see that these two lines are parallel to each other. So this is our parallel circuit. And also a parallel circuit means we have more than one pathway. So you can think of it like city streets. If you wanted to get from point A all the way around back to point B, there's so many different routes you can take. Right? You can go this way, or you can go this way, or so on. A series circuit, however, only has one pathway. So think of it like a highway. Right? You don't have a choice. You have to follow the highway. You can't suddenly, make a left turn. That would be disastrous. And so electrons don't do it in a circuit. Okay, a couple other parts. We have ammeters. Ammeters are used to measure the current in a circuit. And notice that when we attach an ammeter, we attach it in series with the circuit. So the current goes through this is a resistor, by the way. We are in grade 12 physics, we're going to use a resistor to represent any load, because any load that you attach to a circuit will have some form of resistance to it. Okay, and then your ammeter is directly connected in series with that resistor. However, your voltmeter down here is connected across something. And the reason why is you want to measure the difference in energy. How much energy was going in compared to how much energy came out. Did you lose energy or did you gain energy? In the case of a battery, you're going to gain energy. But if you place your voltmeter across the resistor, you will lose energy. Okay? And voltage is a measure of energy for every charge that's going through your circuit. So we have energy and current. But I'll explain these terms in a little more detail later. Now here I have 4 circuits, and there is a problem with each and every one. So, alright, so our first one has no resistor or no load, which means this is a short circuit. And that can cause the wires to heat up very quickly and maybe even cause a fire. So you never want a short circuit. This one, the voltmeter is in series. It should be connected in parallel. This one, the ammeter is in parallel, and it should be connected in series. And this one's just missing a connecting wire. So it's an open circuit. It's not going to do anything for you. Okay. So on our handout, let's try the first practice question. Okay, it's been some time, but what we're going to do is draw a circuit. And we're going to draw a circuit that has a battery connected in series with a motor, 2 lamps connected in parallel with each other. Okay, so let's start with a battery. Battery looks like this. Okay, where the short side is your negative side and your long side is your positive side. Okay, now we have a motor. And then we have, so our motor is connected like this. This is just a one pathway. And then we have 2 lamps connected in parallel. So we want the lamps in parallel. If you remember, a lamp sort of looks like this. Then it says we want switches to control each lamp independently. Now if I put a switch here, you can see that blocks the current completely. And that if I put a switch here, everything will turn off. Because there's no way that our current can actually complete a full closed loop. And you don't have a proper circuit if it's not a closed loop. All right, so let's not get in the way of the motor. So we're not going to put a switch anywhere in here. Now if I put it here, that's going to control both light bulbs. Because the current that goes through the light bulbs can't get past that point. It can't get to either one of them. So what I'd want to do is I'd want to put one here, like that. Now, I could put it here or I could put it here. It doesn't really matter. If I open the circuit on either side, the current can't get through. Right? In this case, it might go through the lamp, but because it has nowhere to go after the lamp, it's actually not going to flow. Okay? You can almost think of, let me just draw a side diagram over here. Let's say we just had one battery with one bulb. And you can think of sort of electrons all throughout here. Okay? And it's almost like they sort of push each other a bit as they go around. Okay? And if I break off any of them here, well, this person can't move forward, or this electron can't move forward, so that one's not going to be able to push it, and so on and so on and so on. So the entire line doesn't move. Right? So if I break it off here, that's okay, because the electrons that are here won't move through it. Okay? And actually, the electrons move very, very slowly through a circuit. A lot of people imagine that it's instant, because you go turn on a light, and bam, the lights are on. But it takes quite a long time for the electron from the light switch to make it through the light bulb. But the reason why it happens so instantly is because you have that lineup of electrons that sort of just get pushed and move around together. All right. So this switch will control this light bulb, and we can put another one over here. Just imagine that I erased that green bit. Okay, right there. So this switch will control that light bulb. All right, so we're going to continue then with some terminology. Okay, now in physics, electricity refers to electrical energy and the movement of charge. When charge moves, we call this current. Okay? We give current the symbol I as the variable in a mathematical equation. And when we measure current, we measure it, our SI units for currents are amperes. Right? So for example, I equals 3 amps, or 3A, capital A. Now, here's an interesting story. So everybody knows Benjamin Franklin. He's famous for sort of, trying this dangerous experiment, although he did it very, very carefully. He was never at any risk of getting electrocuted by a lightning bolt. What he actually did was, yes, he had the kite up into the sky, and yes, there was a key on it, right? But all he did was to try and feel that static charge. So it would have been more like a little shock from if you were to rub your feet on a carpet. Right? It never actually got struck by lightning. He could just feel the charge building up in the atmosphere during storms. Okay. Also, another interesting story, if you guys are like history buffs, Benjamin Franklin is probably the reason America exists today. And that is because during this time in Europe, electricity was like a hot thing. Everybody loved electricity, right? It was like new, and they would have like almost like performances where the public would go and watch these scientists do electrical demonstrations, right? And they'd have like electricity shock from across the room, or it was like incredible. You have these like things turn on, right? So it really was the new and hot thing in Europe at the time. And so Benjamin Franklin was doing all this work with electricity. And so he became very, very popular in Europe. And he actually became close to royalty in France. And so when America started to fight back against Britain, they really didn't stand a chance. Right? Britain was coming in, and Britain was going to win. But because Benjamin Franklin had made friends with royalty in France, France agreed to send assistance to America, thanks to Benjamin Franklin. So if he never did his little kite experiment, he would have never had friends in high places in France, and good chance France would not have helped out America, and America could have very well lost to the British. So interesting side note for anyone who's like interested in history, what if questions. But another thing he did was he assumed that charge moved from the positive terminal to the negative terminal. So he assumed that it was the positive charges that were moving. Now, in reality, today, we know it's the electrons that move, not the protons, and the electrons have a negative charge. But really, it's just a convention. Right? Someone decided to say protons were positive and electrons were negative, but if we went the other way around, physics would be fine. What matters is not that a proton is positive and an electron is negative, but what matters is how like or different charges interact with each other. So even if you were to flip the charges, there's still going to be opposite charges that they will still attract. So, but for the longest time, we assumed that it was positive charges that moved. That's why in textbooks today, including your textbook, we have something called conventional current. And you'll see diagrams like this, where you'll have the positive end of the battery and the current moving from positive to negative. Now that's not what actually happens. What actually happens is something called what we call electron flow, where the current moves from negative to positive. Right? But we're so used to the convention that we used for hundreds of years that it moves from positive to negative that we still use that in textbooks today. And because it doesn't change the result of any experiment, there really is no need to change it, right? So this is called conventional current, and this is called electron flow. Now, we also have two different forms of current. We have direct current and alternating current. Direct current, if you were to plot a graph of direct current, where you have like a current over time, you can see it's very, very stable. It's just constant. And also in one direction. You could think of like everybody doing the wave in a baseball stadium. The wave just goes in one direction, like that. That would be direct current. Alternating current looks sort of like a sine wave if you were to graph it. It's above zero, below zero. Positive, negative, goes one way and then the other way. So it still acts like a wave that moves around the circuit, but the electrons, the movement of the electrons themselves are almost like vibrating. Now, examples of Direct current would be what we're going to do in class with all of our labs with batteries. Batteries provide direct current. However, the outlets that we use when you plug something in, that provides alternating current. Also, just as a side note, if you ever go online and look up the current wars, you will hear about two people, Thomas Edison and Nikola Tesla. Thomas Edison and Nikola Tesla were both geniuses, but Nikola Tesla was a much better scientist and Thomas Edison was a much better businessman. Thomas Edison had developed the DC motor, which was powering houses in New York. I think it was New York, might have been New Jersey, but I mean in that area. Nikola Tesla started to develop the AC motor, the alternating current motor, which was first made at Niagara Falls. And the two of them were battling it out, right? Because, I mean, that's a lot of money, right? Which is going to power the world? Now, obviously, since I just told you that when you plug anything in, it's alternating current, Tesla won that battle. But even though he won because he's the better scientist, he ended up dying a very, very poor man. Whereas Thomas Edison was a very rich man. Why? Thomas Edison was a much better business person. Right? Nikola Tesla wasn't too interested in business, only interested in the science, and so some of the contracts he signed a contract which pretty much sold his AC motor for one fee. Instead of saying like, we will pay you this much for every bit that we use. He sold it all for one fee. And therefore, he didn't own any rights to it anymore after that. So even though the world ended up using his invention, he got nothing after it. So, sad story. But thanks to Nikola Tesla, we have electricity. All right. Let's go on and try example number 2. Here we're doing some unit conversions. So we know that current is measured in amps. And that's the SI unit. But we don't always measure things in amps. Sometimes things are very small. We might measure things in milliamps. And just as a reminder, milli is 1,000. So 1,000 milliamps would be the same as 1 amp. So what we do is if we have 650 milliamps, we sort of imagine a decimal here, and we move it to the left 3 spaces. So we end up with 0.65 amps. Okay, and we can move this one over 3 spaces as well. We get 0.085 amps. This one, if we do the same thing, we get 4.5 amps. And this one, because we're going from amps to milliamps, we're going to move the decimal over 3 places to the right now. So 1, 2, 3. So that would be 95 milliamps. All right, so next thing I want to talk about is electric potential difference. So imagine you hook up an element, like a stove, and that stove is going to heat up. It's going to glow red hot. So as it glows red hot, right, you have current going through it, but if it has energy, thermal energy, where's that energy coming from? And so every charge carries a little bit of energy as it moves through it. And that energy per unit charge is called electric potential. And as it goes through an object, like a load, right, in this case an element, but in any load, anything that has resistance, right, it'll lose some of that energy. And so the comparison of how much energy it lost is your electric potential difference, and we measure that in volts. Okay, and as we went over before, voltmeters get attached to a circuit in parallel. So let's try working with some of our units, just like we did with amperes, but we're going to do the same thing with volts. So again, 1,000 millivolts is equal to 1 volt, but then I also have kilovolts here, where 1 kilovolt is equal to 1,000 volts. So if we said 500 millivolts to volts, well, we're going to move our decimal place to the left 3 spaces. We have 0.5 volts. But if you have 1.5 kilovolts, that's like saying 1.5 kilometers. How many meters is that? Well, 1,500. So how many volts is this? 1,500. Now the last one is going from volts to millivolts. We're going to move the decimal place to the right 3 spaces. And we get 150 millivolts. All right, so I've talked about current, I've talked about potential difference. Now we're going to talk about resistance, even though I've mentioned resistance quite a few times. When you have charge pass through a material or a device, they will experience resistance, almost like a frictional force. Right? And that gets converted into thermal energy. So if you have something like a toaster, you might want to have a lot of resistance in that toaster, because then that gets transferred into heat, thermal energy. Same with the element on the stove. Okay, but the same thing happens in an incandescent light bulb. An incandescent light bulb is made to have so much resistance that it reaches temperatures of over 1,000 degrees, so that it's so hot it glows, just like the element on your stove. But it's actually hotter than the element on your stove, because the element on your stove is only going to glow red. These will glow white hot, which is why if you've had an incandescent light bulb on for a long time, you don't want to go and touch it. Okay? And this is also why they're extremely inefficient. Most of that energy you're putting into it is being converted to thermal energy, not radiant energy. Okay, but that's another example of electrical resistance. And we measure electrical resistance in ohms, and we give it the symbol omega, which kind of looks like a horseshoe. Resistors look like this. You have them in your pack. You have ones that look like this here in your package. I actually gave you each 3 resistors, and later we'll determine how much resistance each one actually is. But since we've talked about voltage, current, and resistance, we're going to put them all together and mention Ohm's law. So Ohm's law is a relationship between these 3 variables, right? Which pretty much says if you have a graph of voltage versus current, the slope of that graph will be your resistance. Or another way, voltage over current equals resistance. And I have a little triangle here for us to be able to easily rearrange that equation. So let's try an example with this. Example number 4. Calculate the resistance of a load with a voltage of 25 volts and a current of 410 milliamps. So let's write what we know. So the voltage is 25 volts. And the current, remember we label current with the capital symbol I, that's current. And it's 410 milliamps. But when we plug our units into Ohm's law, we want to have the base unit. So we need to convert milliamps to amps. That's why we practice doing that. So this is going to be 0.41 amps. Okay, and it wants to know resistance. So if we looked at our V equals IR. And if you want, you can put a triangle on there, where V is up here, I is here, and R is there. Resistance would then be equal to voltage divided by current. So if we go here, we'll write resistance equals to voltage divided by current, which is 25 volts over 0.41 amps. We get a resistance of 61 ohms. I'll just pause there. Okay, now number 5 is continuing to use Ohm's law, but we're going to fill in this table. So in each column we either have current, voltage, or resistance. I'm giving you 2, then you have to solve for the other 1. Sometimes you may have to change your units, like this is 25 milliamps. We will have to write that as 0.025 amps. And then give it voltage. Again, we can use our triangle. Right? To find resistance is voltage divided by current, which would be 12 divided by 0.025, which is 480 ohms. So I want you to take a minute and try to fill in the rest. Once you've done that, you can check your answers. I'll fill them in. Alright, so before we start our first lab, I wanted to teach you how to determine what the resistance is on a resistor. What we're going to be doing is learning to read the color codes. So on the resistors that we have, right, there are 1, 2, 3, 4 bands. Some resistors have 3, some has 5, ours have 4, like this. So how to read the resistance? Your first band is the first digit of your resistance. And depending on what color it is will depend on what that digit is. Alright, so let's take an example. Let's say we have, I'll just make up my own color here. Green, orange, brown, and then gold. So let's say this is the colors on our resistor. So the first band is our first digit. So you look for green, and that's a 5. So our first digit is going to be 5. The second band is your second digit. So in this case it's orange, so we look for orange, and it's a 3, so 3. Your last band is your multiplier, meaning times 1, times 10, times 100, times 1,000, times 10,000, times 100,000, times a million, and so on. In this case, it is brown. So brown is times 10. If it's times 10, we're just going to add 1 0. If it was times 1, we would do nothing to it. If it was times 100, we would add 2 zeros. Right? Times 1,000, you'd add 3 zeros. So it's pretty much saying 53 times 10. And that's 530. And that's how many ohms there are. So this resistor would be 530 ohms. Now when you have a resistor, it's not perfect. And nothing can be perfect, right? It's not going to be always exactly 530 ohms and never deviate from that. It's not going to happen. Depending on how well it's built, there'll be either more or less deviation from this value. Now this is called your tolerance, and that's your last band. And our tolerance for the gold one is down here. So plus or minus 5%. That means your resistor is 530 ohms, but it can be slightly less or more than that by a range of 5%. Now in this class, we're not going to worry about that. We're just going to take it at the value that the first three say it is. So when we do our lab and you read the resistance, you'll look at the first three and you'll follow this color code. Okay?